Hey guys, welcome back to my YouTube channel, and I hope you're finding these tutorials to be useful and educational. Now, in the recent few videos, like the last 15 to 20 videos, we covered the topics of deep learning and neural networks. We did image classification using convolutional neural networks, or CNNs, and we did image segmentation using UNet. And in the last bunch of videos, we actually covered the topic of autoencoders and a few of its applications, like image denoising and image colorization and anomaly detection and so on. Now, in this tutorial, in today's video, I'm going to basically convey one simple message, which is don't waste your time doing any of these deep learning if your goal is to use it for your everyday image processing tasks. If you want to denoise your images, then there are probably better ways to do it or faster ways to do it. If you are interested in image colorization, image segmentation, classification. In fact, I published some of my earlier videos. If you look at them, you can see how traditional approaches can be far more efficient way of doing your tasks, and not just efficient, but most of the time they turn out to be far more accurate compared to deep learning. Now, deep learning is getting there, but that's not the answer to your everyday challenges with image processing. Of course, one day if you would like to work for NVIDIA's or Adobe's or Google's and Facebook's of the world, then it definitely helps to learn this stuff. Now, in fact, it definitely helps to learn all of the deep learning and neural networks, because that's only when you can tell that that's not the tool that you want for this task, right? You have to know what you're rejecting in this case. So, and it's always important to train yourself on various happening things out there. Now, but when it comes to applying, the technique, then please beware. Do not apply deep learning where it's not really needed. Okay, so for example, image denoising. So in this tutorial, I'm going to just show you 3 or 4 examples of, for example, denoising or image colorization or image segmentation, for example. I'll just show like literally how you can solve these with 3 or 4 lines of code and get very good results. So again, based on some of the comments that you guys are leaving on my YouTube feed, it concerns me a little bit, because it feels like you're trying to use deep learning where it's not really relevant. Yeah. So if you have like millions of labeled images or thousands of labeled images, then you probably would be achieving the task that you're trying to do with deep learning. But I really don't want you guys to waste your time working on something that may not be an ideal solution for your job. Okay, so let me jump into the Spider interface we can actually look at a few lines of code to do everyday tasks. And the tasks I'm showing you are completely based on the YouTube comments that I actually got from you guys. Like someone asked me about denoising. How can I do this? Blah blah blah. Right? I'm like, don't do autoencoders. What you have is an image that can be easily denoised using traditional means. And if your image looks crappy to begin with, no one can help you. Go collect another image, a better image. But don't try to fix crappiness by doing all of this stuff. Okay? And I'm not saying whoever left the message, you have a crappy image. I'm just mentioning that, okay, this is sometimes you just have to go back and collect new data, because existing data is not good enough. Okay. So someone else asked me about colorization. Someone else asked me about segmentation. And for all of those tasks, I'm like, okay, you can easily use existing knowledge in image processing, whether it is OpenCV or scikit-image. So anyway, that prompted me to record this video, and I hope you learned something even from this tutorial. So let me fire up the Spider IDE, and then just let's colorize a couple of images, okay, using traditional means. Okay, so let me zoom in a little bit more so you can see it with no issue there. So let's start by image colorization. Again, I'm not going to go through every little step, because maybe I'll record other videos in future talking about every one of these steps, and if I haven't covered already in one of my previous tutorials. But let's take this image as an example. Now, If you really have, let's say, outdoor images, that are black and white, and you would like to colorize them, you have like your old grandparents' pictures, you want to colorize them, then maybe deep learning is a good approach, because by training it on a whole bunch of people and outdoor images, you're guaranteed to get like your skin tones of your grandparents correct. Although I should mention, I tried this with my grandparents and my own childhood images. Looks like they trained these images on a lot of Caucasian, skin tones. So all my grandparents kind of look a bit too on the lighter skin tone side than they really were. So it wasn't even accurate. Yeah. So it's not trained on. It'd be cool if they can recognize the facial features and kind of identify at least like some sort of an genetic or origin, in general, to actually get the skin tones right. But again, I don't know. Nowadays, everything is political, so maybe someone thought about it and didn't even want to go there. Okay, getting back to our focus, our topic here. So for microscopy images or any scientific images, usually we don't have that problem, right? We don't have the problem of, oh yeah, this is this and this is in real life like this color. The sky is blue, why is it showing it as like deep green, which never happens. And although it kind of happens if you have, a bunch of radiation, scattered by our Earth's magnetic field. Again, sorry for going towards physics, but again, getting back, focus. So most of the scientific images, they're grayscale, or you don't have like some natural color. Some life science images, probably it makes sense to colorize something in some colors. But let's say you have an image like this. How can we apply false color? And now I can basically, one way to do this is say my black, instead of black, I'm going to call it blue, and my white, instead of white, I'm going to change it to red. Anywhere in between, it's going to be a mixture of black and white, or sorry, blue and red in accordingly. Okay, so that's one way of doing that, and you can do that very easily in Pillow. And I copied a few lines of code from my notepad. Again, we are going to open an image first. And let's open the image as gray. I mean, this image is gray to begin with, but I'm not sure. I downloaded this from the internet, and I think it's an RGB image, even though it looks gray. So I need to convert that into gray level. So this is how you do it in Pillow, and one single line to actually colorize this. And the way we do this colorization is again, image ops.colorize. There are a few of these image operators or options. I don't know what ops stands for, but colorize is one of those. And here I'm defining my black as blue, and my whites redefining black and white levels basically. Okay, and let's go ahead and show this. And when we run this, it's on my other screen. So let me go ahead and drag it. Oh, there you go. So here it is. So as you can see, my black is now blue, my white is red, and somewhere in between is a mixture based on how much black and white mixture that is. So this is an easy way of colorizing, and if you want like more creative ways, of course, OpenCV has a bunch of ways to do this, and Scikit-Image has a few ways. Let's actually do OpenCV, okay? Import, and let's unfortunately I'll have to type it because I haven't planned on showing you OpenCV, but it's pretty easy, so why not just go ahead and show you. Okay, so let's go ahead and read the same image. I think I call this bsc.jpg, and let's also read it as gray level image. Okay, and let's colorize it. My color image is nothing but cv2.apply. There is something called apply color. Okay, apply color map, and to what? We are applying this to our gray image, and then what type of color map do we want to apply? So let's do color map. One I like is called jet. Let's go ahead and do that. Okay, and the cv2, this I have written down because I use this all the time. So cv2.imshow, let's go ahead and do this. Color image, wait key, and then let's run it. It should open it. There you go. Okay, so now it's actually applying the jet color map. There again, Google search for various color maps under OpenCV, color maps under PyPlot. They also have a whole bunch of color maps. Now you can go ahead and save this image to retain these colors. So this is again easy colorization. Again, you do not need any deep learning. This was like instantaneous, fraction of a second, and you can easily colorize images, provided you know what type of color scheme you would like to apply. Now let me show you a couple of ways to denoise images. Okay, and this too would be pretty quick. And for denoising, my favorite denoising method for microscopy images is called non-local means. Non-local means, I already covered a video on denoising, so please go ahead and look for that video in my channel. But I'm going to quickly show you a couple of very easy, fast ways. You know, Gaussian smoothing is one. Of course, this is not technically, well, it is denoising, but this is in a way it smooths the image. So not really the best all the time, but let's go ahead and do that. Okay, so again, one simple line. This is nothing but, again, you read your image any way you want. You can use OpenCV, scikit-image, it doesn't matter. I'm converting this to float because of course we are going to do some math to the image, and whenever you do that, it's always good to convert your images into a floating point. Okay, so let's go ahead and run this. And again, the actual thing that's doing this is in ND image under SciPy, and there is a Gaussian filter. Again, Gaussian filter is in OpenCV. I think it's also in scikit-image. I'm just using one of those. That's it. Yeah, the one from ND image. So when we go ahead and run this, there you go. It looks a bit blurred, as you can see on the right-hand side. Again, I could have saved the image and showed you the image, but you get the point. You know, this is a denoised image. In fact, in this case, I'm using a noisy.jpg. And here it is. This is the image. And as you can see, got kind of denoised, but also got blurred. Non-local means actually retains the edges. And the other good one, actually, if you don't think non-local means is working for you, another one that actually works very well is anisotropic diffusion. Okay, this is again, it works under the principle that, okay, there's a diffusion going on, and again, you can look at online documentation for this, but I've written a few lines of code in my notepad, so let me go ahead and paste these lines here. Okay, so all it's doing is in the medpy.filter.smoothing, there is anisotropic diffusion. In fact, if you want to write your own anisotropic diffusion algorithm, you can do that, but it's already available as part of medpy package, so I'm just calling that function. Okay, and the number of iterations, how many times you want this diffusion to go through, kappa value, gamma value, and then option 2, whatever, you know, for you can actually check the I'll try to share this code on GitHub as soon as possible, but until then, let's go ahead and look at this. In this case, I'm actually saving the result as anisotropic result.jpg, so I can, again, let me go ahead and open that image. There you go, and where is my input image? Here is the noisy image, and hopefully you can see the difference right there. Okay, so now it's cleaned, and it retains the edges. The edges are not. So this is kind of like non-local means filter, and actually this works equally well. I have never compared these two. It'd be nice to compare them, but then it comes down to specific use case. So okay, so again, any of this is literally a second or a fraction of a second, right? I mean, we just hit run and then you get the result. But the same, if you would like to do denoising, first of all, you have to find 1,000 other images that look very similar with similar noise. Okay, by the way, when you add artificial noise for deep learning, then it tends to work very well on images with artificial noise, but actual real noise coming from microscope image acquisition, usually it doesn't work very well. That's again one other reason why don't even try. Okay, if you don't have enough training data collected exactly the same way as your other images, future images are going to be. So here is again a very easy way of doing denoising. Again, these are the two examples. The reason I'm showing this is because I covered this as part of my autoencoder topic. And what else shall we do? Let's actually do segmentation. Again, segmentation is a simple segmentation. Like if I take this specific image, if I come back and show you this image, this is an easy one, right? So I can say values below 50, for example, are all one region. Values around 100 are another region, like 150 another, 250 or above, or 200 or above is the bright region. So it's histogram based is very easy on this specific image. But what if you are working on something like Scratch Essay? Again, I made a video on this topic in the past. Some of this I'm repeating myself. But Scratch Essay, if you look at this image, so you can see, I hate this paint. I should go back to a different viewer. But anyway, so you look at this. It's a very difficult image to segment because it all looks pretty much the same gray level. But we know that this region here on the sides actually, can I zoom in using Control V? Okay, let's do that. Okay, there you go. So the regions on the right and left, they have a lot of texture. The region in the middle doesn't have texture. So we can actually use image filters to highlight the texture and then filter and then segment the image. Again, this can be easily done with machine learning, with deep learning. All you got to do is take generate a whole bunch of filters coming from this region and this region and so on, and then the machine learning can easily do this task. But do you really need it? You absolutely don't need machine learning to segment something like this. Yeah. So again, I've written some code already, so we don't waste time. So let me go ahead and paste it. Importing the required libraries. I may not even need a couple of these. For example, yeah, I'm using Otsu. Let's read the image. I just showed you the input image, and entropy image actually helps if we progressively look at these results. So let's actually look at entropy image. Any physicists out there, you probably know what entropy is. Entropy is a measure of disorder. And if you look at this, the original image I showed you earlier, the region where you have a lot of texture, there is a lot of disorder, right? And the smooth regions, less disorder. So entropy is going to highlight. So again, let's actually run the code only up to this point so you can see what I'm talking about. Okay, so you can see the entropy is very high on in this textured regions. It's very low right in this middle region. So what if we can look at the histogram of this entropy plot and then perform an Otsu to find where that separation is, so we can separate these two. Yeah, that's exactly what we did. So the next step is threshold using Otsu. So let's go ahead and there and look at my thresholded image, and now you can see how it all, well, oh, this is just the values. Okay, the threshold is nothing but it's telling me the threshold value is at 2.13 something. Okay, so obviously I cannot plot it, but what I can plot is the binary image like I'm doing here. So I'm taking the threshold value and saying that, okay, anything that's below the threshold is convert it into a value of 1 or 0, right? So that's what I'm doing here. Convert my threshold into a binary image by selecting all the pixels only that fall below this threshold value. So now when I actually print this out, now you can clearly see how this scratch region is, or this flat region is well segmented from these other regions. Again, with literally 3 or 4 lines of code, we are trying to do these advanced things that machine learning people kind of tout about. Okay, again, there's a lot of reason to be proud of machine learning and deep learning, but for tasks like this, don't go to machine learning by default. Okay, so just to finish this off, again, this other image I just showed you, how would you segment that? Again, pretty simple. Read the libraries. I'm actually using my BSC image again, which is nothing but this image. Okay, and usually if you use histogram, that may not work out very well, because if you look at the gray, the regions, again, it's worth mentioning. Sorry for belaboring this point, but if you look at these regions right around the grain boundaries, you see how they have like this bright region. So that will be segmented as something else. That would be segmented as some other region if you're not careful. So Otsu can be pretty useful, but traditional Otsu is only designed for binary separation. There is a new, I think in scikit image 0.16 or later, or just install the latest version of scikit image, you should see threshold multi Otsu. Okay. And if you use that, then you can actually define how many of our classes. Let's say I want to segment this or find only 2 classes here. And let's run this, and this will be segmented into only 2 different regions, right? But in this case we have 4 regions, so let's go ahead and do 4. And if you run the code, you can see how my image is instantaneously segmented into 4 regions: the dark, medium gray, light gray, dark gray, light gray, and then this bright region. Okay, so this is how easy it is to do things in a traditional way. Okay, so in summary, do not waste your time with deep learning if you know that that's not the right tool for the job. And how do you know that it's not the right tool for the job? Look at the traditional approaches. If it gives you decent results, why use deep learning? And yeah, don't try to fit it into your research if it doesn't belong there. But please do learn about deep learning, because it's very important to understand exactly what the strengths of this approach is and what the limitations are, so you can evaluate where to use it and where not to use it. I hope you found this tutorial to be very useful. If so, please go ahead and subscribe to my channel, and I really appreciate your attention and you coming back and watching these videos. Thank you very much.